Hey folks, so this talk is actually was scheduled to be given by a colleague of mine, but he's not able to travel. So he and I worked on this thing. This is something which was a very peculiar request from one of our very highest QPS serving customer. And the problem which they came up with was consistently P99.9 is coming out to be very high. And they were saying because of that, they did some analysis and figured out that the revenue at a particular time when the P99s jump for Uber Eats has been dropping consistently, and customers are not placing orders because of minor jumps in latencies at the P99.9 level. So this is something which we worked on, and we realized that this needs to be solved. And when we tried to search on the internet as to how people are solving it, the most popular thing was this thing, which is called tailed at scale. This is actually a paper by Jeffrey Dean and Luis Andres Barreso. What this actually says is that if you have 100 requests flowing in parallel and one of them takes very long, then the whole process would somewhere get slowed down. And if you're measuring just the P99s, you might not figure out that there is an actual problem at a very peculiar place in your code. So user retention is very, very sensitive to response time. Since our customer, Uber Eats was one of our biggest customers, and they were saying that if the time to load what all is there in a store for even one customer is very high or somehow spikes up, that customer is expected to not open that particular store again, which is actually, so people are noticing that, and they are saying that it is happening for the most popular stores. So somewhere down the line, our revenues might get impacted. So improving the tail latencies at this level was expected to cause a huge impact. And when the analysis was done, they said that a particular drop at a particular time can also cause thousands of dollars of revenue fluctuating. So mitigating tail latencies was considered to be the thing that we had to do. So short term, we realized that request hedging and tying request was what we should do. The long-term solution is still being debated at Uber, still not finalized, but the short-term solution has worked really well until now. So, as to explain you guys what is request hedging, before that I'll explain to you guys that right now in Uber for Eats-related systems, we are using Sharded MySQL using Vitess, and Vitess actually has something called VT-gate, which you can consider as a normal proxy which routes request depending upon your sharding key to different shards and then collects out the information and sends it back to the customer. So it's like a transparent proxy layer, and for the customer it would be like on single MySQL database, but internally it will go out and query from other shards. Now, what is request hedging? So request hedging, if you explain simply, was that we'll make a request, and if it takes longer than a particular defined threshold, then we'll duplicate that request to other tablets, tablet meaning other read replicas. And we'll get from wherever we get the fastest response, we'll take that and we'll send it back to the customer, and we'll cancel all the remaining requests. And hedge time was the time at which we would say that if you have crossed this time at the VT-gate level, so let's say the query hits VT-gate at T0 and our hedge time is 100 milliseconds. Within 100 milliseconds, if we don't get a response from the first replica which it had to reach, we would actually go ahead and spread this request to different replicas, and then we'll see which one responds faster. As soon as we get a response, we'll cancel the request to the other replicas. Now this created one big question, was that if we are serving, let's say 1 million QPS at a time and 10% of our requests are slow and we start doing hedging, we might overburden our system as well. So we figured out that we will actually not hedge all the requests. We will figure out, so later in the slides you'll see that there are actual ways to tag that I want this query to be hedged only, and I want this query to be hedged after this time. This is the percentage of times I want this query to be hedged. So,
but also, isn't there a strong correlation between bad queries and slow response time?
Yes. So that is also one thing. So depends. So for bad queries, we actually had a particular system which was always tailing our MySQL slow query logs, and at Uber the slow query time limit is 0, so every query is getting logged and it's being used. So we were using that, and we had a system which used to actually flag such bad queries, create a Jira ticket, ping the customers as a bug with an SLA date. So those things were already being done. But even after doing that, our customers were saying that even for the queries which are not being caught by your system, which are being told to be right, you're not able to see complete results, as in the P99.9 is still bad even for a query which you say is good. So there is either some problem at the host, some problem at the network, or there is some bad actor somewhere, but it's impacting the overall latencies which they cannot afford. So the implementation was very simple. It was we just figured out that okay, we need to start a timer, and if we don't get a response, then we will figure out what all tablets to reach, and then we will fire them as go routines and get those requests back. So this was done in the VT-gate layer, and so VT-gate is just like a proxy. So I think this can be implemented back in proxy SQL layer as well, but we implemented it in our VT-gate layer because we were relying on Vitess. Now these are what things which we called as how do we tell the VT-gate layer when to hedge, what to hedge, how to hedge. And we started with custom comments, then we figured out that in Vitess there are actual standard directives. So we started using directives, we created a new directive which is hedge timeout. So if this query takes more than 20 ms, that is the point at which the proxy layer would say that no, instead of just going to one random replica, I will now figure out other replicas and I'll fire the same query there and I'll see who responds fast. Then the question was that let's say you have 20 replicas and you try to reach replica 1, it was slow. Now will you reach all the other 19 replicas, or what will you do? The customer wanted to control it at their level, but they wanted to control it at a query level also. So for some queries they didn't want to reach many replicas, but for some queries they wanted to reach many replicas. So we added other customizations called number of requests to hedge. So this would actually tell that how many requests additionally, so how many additional replicas we could contact. Then there was that if the pending request should be cancelled or not. For some analysis, some of our customers said that you don't cancel the request at all. Let the system be overloaded and we'll see, or we'll do some analytics and figure out what is happening even if the system is overloaded somehow. Then the most debatable topic was probabilistic hedging. So to roll it out fast, what we did was we created something which was probabilistic hedging. This was nothing but it was like flipping a coin, and if the number, so the coin would return us a number between 0 to 1, and we'll divide it by I think some percentage, and we'll see that okay, if this percentage is less than this, we will hedge it or will not hedge it. This was something which was not treated or taken very well, and then we were asked to actually implement something called a budget based. So from probabilistic we had to move to a deterministic way, where our customer would say that only hedge 10% of my requests, and that 10% should also have prioritization built into it. It should not be like a random query comes, you flip a random int.64 function and you figure out some number and say that okay, we'll go ahead and hedge it or will not go ahead and hedge it. So the problems were that with probabilistic model we were doing uncontrolled hedging, and we were not able to have a strict budget of saying that we'll throttle deterministically 10% of our queries. It was that even if you specify 50%, whatever that random number returns would actually lead to the number of queries which will finally get hedged. And the flaw which I pointed out was that we were generating, so what we were doing was this rand.int n 100 smaller than probability of hedge. And this was actually inaccurate and failed to hedge requests that should have been done. But this was the V0 which we wanted to do a POC on to see if this concept even works at their scale. So the concept worked, but we ran into this problem which needs to be solved, which was that we had to do a budget-based request hedging. So I'll pause for questions if people had, because after this there would be a few slides which are too much maths.
So what happens if none of the replicas then replies in a threshold? Like you want to hedge and try different replicas, but those also don't reply. What's after that?
So after that, the only thing is that we emit metrics that this particular query is getting unresponsive. So what we have is we have something which is called a query timeout as well. So after 30 seconds, we'll anyhow cancel the query irrespective of whatever happens. If you're not responding in 30 seconds, which is a very large timeout, but we'll still cancel it after 30 seconds. But if you are taking too much time or it's getting flat, so above 1 second is something which our own monitoring and metric system also flags a query to be. So our dashboards, and we have a system which actually tails our slow logs, then creates Jira tickets out of those queries. So it will start catching them and it will start reporting it to the customer, but the query serving stack will not do anything. We actually have something which is called a throttling system, which would later on start to recognize all these queries which are very slow and would start throttling them. So the customer would actually get responses back that this query is being throttled specifically. But that would take some amount of time to kick in. It would take maybe in some cases hours if the query's QPS is not that high. So
is this being implemented in the possibility of caching? Like even with caching, you still have this problem. That's why you need.
Yes, even with caching, we have had this problem. So this is actually being done so that even after missing our cache, somehow our P99.9 does not go too high because of one bad host or some network issues at our end or some network issues between the proxy and that one particular replica. So this is just a way to increase our options and see if we can find someone who is faster or not.
The mitigate implement change, it's available upstream?
It's not available upstream, but it's in discussions to get available upstream because there is not. So this implementation is something which we are still fine during this budget-based hedging thing, because we don't want to release something which is a random coin flip in the open source system, because if somebody does end up using our product, they would. So even we could not justify what happened because we would not know what is the random value which was generated at the time of the request.
Can this make the whole system unstable? So if you basically, if there's, let's say on the front side, there's kind of denial of service attack that's creating millions of requests, and then the whole system gets slower and slower. And
yeah. So the thing is that this entire system would only do hedging when your query actually has the tag to hedge. So not every query is hedged. The customer actually dictates. So if you see, if this query comment is not there, hedge timeout MS will not hedge, and you have to specify the number of replicas you want to reach, will cancel or not, and what is the earlier we used to say what is the probability of hedging. Now we take a strict budget which is like X% of queries that we want to hedge. So like limit the number of hedge requests to a certain budget, that is hedge less than K% of requests over any particular time window.
Do you collect any heuristics or statistics about which nodes are frequently not meeting the targets?
Yeah. So those metrics are also collected. In addition to that, we have metrics that this particular query is always getting hedged from this particular host, and these are the queries which are these are the hosts which are responding the fastest. In addition to that, we also actually have some alerts that, let's say you have given your hedge timeout to be 200 milliseconds, and every time this query comes, 90% of the times it is still getting hedged. So we do emit metrics and alerts to our customer that maybe 200 ms of hedging is too aggressive. This query is expected to be slow, but you are expecting it to be fast and you are overloading the system. So we do have metrics and observations in place to actually report that. But there is no smart analysis that the system would itself figure out that, oh, this should not be hedged, and it will start not hedging it. Those things are not there in place here.
How do you determine how many replicas to hedge? And then are those replicas spread out, across different data centers? How does that work?
So replicas are spread out across data centers, and what we actually try to do is not to reach out the replica in the same data center as the one we already tried to reach out to, assuming that there is some issues, and we have around 3 AZs available per region, and we have 2 regions. So we have around 6 availability zones to reach out to for any particular replica, for any particular query as such. The other question, can you just...
How do you determine how many replicas?
Yeah. So the first draft we started with our customers actually directing how many replicas we should hedge onto, which is something which is provided here. The number of additional requests need to be made is something which the customer should actually provide us. But based on the heuristics and the metrics which we get, we do publish few analyses and few metrics. But right now also, the MySQL team or the platform team does not dictate how many requests you should go to. The system only suggests, it will never dictate or override what the customer is saying.
But that one is showing the number of retries of the queries.
No,
It
so
doesn't-
the number of additional requests, so number of hedge requests is that, let's say you have 5 replicas and you fired a query and it didn't respond in, let's say, whatever the timeout was of 200 milliseconds. Then number of requests, hedge requests is number of tablets I will reach in addition to this particular tablet. So if number of requests hedge is 3, your first request will go to replica 1, didn't respond back, then it will reach out replica 2, 3 and 4 in parallel and wait for the fastest one. Either replica 1 would reply or someone in 2, 3, 4 would reply.
So continue the discussion about maybe overloading the system. Since you've contributed a throttler implementation to Vitess, it sounds to me like the reasonable next step to have a
Yes.
throttler pushback
Yes.
against.
Yeah.
hedging.
So every hedged request actually goes to the throttler as in the lowest priority to be served as well. So
Which of the throttler? The query throttler?
the query.
Oh.
So once it is, so since we know what we are, so we are the ones who are firing it to be hedged, we actually pass those metadata tags to the throttler, to the query which reaches the throttler also. So there is actually a component after this which is there in the open source world called a query throttler, which actually takes something called a query priority, which is a number between 0 to 100. And if you specify it as 0, the throttler will not even do anything. And if you specify it as 100, it will try to actually do every check possible to see if firing this query might overload the system actually or not. So these queries which are hedged are then, so which are decided to be hedged are actually passed at the priority 100 to the throttler, so that the throttler can actually make a decision that no, there is a problem, you are actually overloading the system by hedging. So that is our second defense. But as of now, since this is not that, so it's only being used by a subset of our customers who actually require P99.9 to be used, to be checked, and we are not seeing any overloading happening because of this. That also might be because we have done a lot of fine tunings and a lot of experiments to figure out the right number also, which is there later on in the slides. But this would, if you don't have a throttling layer, this would actually, this is expected to throttle your system or overload your system unless you enable the throttler. That is why the throttler was merged first, then this needs to be merged.
That was one of the main purposes of the throttler?
Not the main purposes. Main purposes were still that, so our customers were actually, so whenever we used to get a page that the system is overloaded, the first response would be that we cannot fix it right now. You own this piece of system, somehow fix it, do anything but you fix it. And without the throttler, there was nothing at our end. We used to rely on our customers saying, you please do a deployment, do an emergency deployment, do something. So now we actually control the thing. Now we are actually also trying to implement something which would block a particular query from the throttler. But that is expected to release later. So our core challenge was that we had to accurately track that the hedge request and the total number of requests over a particular time window, and we didn't want to. So there was one thing which was an obsession at our org was not to use locks anywhere in the hot query path, because our experience with using mutexes and locks in the hot query path was not great, and it was not great exactly for this customer who reached out saying that the moment we added locks in the query throttler, his P99 and P99.9 spiked. So there should be no locks or anything in the query path, and that was one of the major requirements which were asked. So our approach was to use lock-free atomic, so it's not entirely lock-free, it's still atomic in 64s. So what we used to do was, now what we do is we keep counters of requests, which are the total request and the number of requests which are hedged. And then we have a exponential decay related window approximation, where we actually do this. So the formula is that the new count is old count, so the number of requests which are already there, into the decay factor and the number of new events which have come. So if you see, this is how it will look if you receive 100 requests at T0, after a decay of 0.9 at t0 it will still be 100, but at t plus 10 it will shut down to 35% only. So with time will actually, so that graph will actually show that with time will, with a 0.9 decay factor, you will actually reach that stage. Now this is the calculations which we use. So our decay interval was 1 second and the decay factor was 90%. So we kept 90% of the request at particular time in it, and with time we used to forget the rest 10%. So we were still decaying exponentially with recent events having the highest weight, which is 1, and the weight after 10 seconds would be 0.35. Calculation of the effective window was actually negative times the decay factor divided by decay interval divided by the logarithmic value of the decay factor. So we actually did a reverse calculation. We wanted this to be 10, and that is how we tweaked these numbers and figured out that if we want 10, we should start with a decay factor of 0.9. This actually helped us because the counts only depended on the current value and not the history. So one actual question was actually this: why did you use exponential decay and not traditional sliding windows or fixed?
Can you just go back to the formula? The decay value formula. One slide before. I think it was one slide before that. Yes, new count, old count, times decay for these new events, but new events could overwhelm the decay still.
Yes, so this system actually has a 10% probability of error. This can still cause, so this is just an approximation, it will not, so if you have new counts which are too high, then your sliding window would not actually degrade like this, it will still almost be the same. So that is one thing which we are still trying to figure out. It is not the right, or as in the completely silver bullet which is or the right solution. This is just one thing which is right.
But in that case, a throttler will come in.
Yeah.
Like if your new events are overwhelming system, then the throttler is supposed to take over and starts throttling.
So even if you look here, we are saying that the disadvantage is that in 10% of the situations we saw that it was not respecting its budget. It was still going ahead and it was querying the system, but our throttler was actually working in these situations and it was helping us.
One more question. When do you reset the counters?
So the counter is reset at decay interval. So while this system had a disadvantage of errors being there, it would not always work. So if you say that you want to throttle 50% of a request all the time, it might not happen. There is a scope of a 10%. 10% of the times it will not hedge, or it still go ahead and hedge. But since we had another layer of defense at the throttler level, which would actually figure out that the system is getting overloaded, we were okay with this because for us, this was a very important factor. We had to be log free and we had to be high performance, because when you are trying to solve P99.9, you cannot add more overhead of performance just to solve performance itself. Now, this is just a random experiment we did to prove our POC works fine or not. So this was a sleep statement where what we did was 1% of the time the query would sleep for 100 milliseconds, and the rest 99% of the times it should sleep for only 1 millisecond. And what we did was we did no hedging, and we saw that the P99.9 was 110 ms, which is expected because we are sleeping for 100 seconds in 1% of the situations. And then we did a hedge time of 10 milliseconds, and we saw that our P99s and P99.9s did improve. That is because at the 10th ms window, it actually went ahead and fired the same query on 3 other replicas, and on one of these replicas, it would just sleep for 1 second and return back. So we would get a 11 ms.
So in this table, how do you evaluate the impact of the throttler?
No, this is just the POC for the. Here the throttler was not there. Throttler will be in actual production when the new event coming in. It's an open close.
So this table assumes that all queries that needed to be hedged were
First,
hedged,
yes.
and then measuring the best
That's
response time.
yes.
This is just the POC.
Okay.
Then these are the metrics which we started with. So our first metric was number of times the timer went off, as in the number of times we did hedge a request. And then that was the hedged first count. So refers to the number of times the hedged request responded before the parent request message. So we were actually seeing that, so if you see, this is a benchmark cluster, and we were seeing even in our benchmark clusters, the hedged count and hedged request to be very high. Then, so the first thing was we started with that random query. But then we wanted to actually try it on a particular cluster which was used as a benchmark cluster. So the benchmark cluster actually had a QPS of 14,000 queries per second from the client itself. And what we did was we bombarded it with random slow queries, random queries which should take time so that the system overall slows down. So without any extra artificial query load, the system was performing with a P99.9 of 70 ms. This was a benchmark cluster of the customer itself. And then what we did was we added artificial load of random queries which should actually hold out the threads which are running, because we were artificially injecting slow queries in the system. And then we saw that the P99s were actually getting significantly impacted, P99.9s, just because we were injecting some random queries in the system. And this is an actual graph of that same benchmark system. And before this, you can see that the system was actually going at a P. So P99.9 was going, I think this is the average value of 195 ms. But if you see, as soon as the hedging time was set to 90 ms, the graph from these peaks actually just started to have smaller peaks. So this actually proved that even though this system has a 10% probability of things which should not get hedged, getting hedged, or which should not be hedged but hedged, but it was still protecting us from all these spikes. And these spikes were what our customers were saying to be the biggest issue of customers. So their customers dropping off because of these spikes. So if you see, this is a benchmark cluster, and then we'll show a production cluster as well. So this is our production cluster. Hedging helped reduce the P99.9. So this is actually a screenshot of a customer email which was sent across Uber. And this says that the hedging reduced P99.9 by almost 20%, from 107 ms to 92 ms. And they had spikes of 500 ms. Now the P99.9 is pin flat. And if you see, this is actually before, and this is actually what happened after. Now, how to choose hedge time was something which was debated, benchmarked. Many people had different theories, released something. People did their own level of POC, and we finalized that this is what we should look into when we are choosing a hedge time. So a large hedge time was showing us there were no observable benefits at all, because by the time you expect or you want this query to be hedged, in most cases that query was getting a reply from the original tablet it was supposed to get a reply from. And if we had a very small hedge time, we were actually increasing the overhead and overloading our systems. So our throttler alarms used to go off randomly, that somehow something is happening, somebody has changed the hedge time and it is causing an overload. Now what we realized was, to improve the kth percentile, the hedge time should be so that the 100 minus k percent requests get hedged, and that is where that value would be the right hedge time to use. Now relationship between the hedge time and hedge query ratio was, this is a simple math, that if your hedge query ratio refers to the change of hedge counts to QPS, and if we increase the hedge time, then the number of requests which would get hedged would decrease, because you are now saying that you are okay to sustain, let's say, a larger time of P99.9. But as and when you start reducing it, you will start having a system overload. But if you protect your system from that overload, you would actually start performing very well like this. I think yes. So this was it. I think if there are any questions.